Lab objective of this lab is to implementation and analysis of moving average filter and implementation and analysis of finite impulse response filter Fourier transform design method. In task 1, which is the defined filter, a filter in a context of DSP refers to a system or algorithm that modifies the characteristics of a digital signal. Filters are used to extract, enhance, or suppress specific components of a signal based on their frequency, amplitude, or phase properties. The second point is types of filters. Low pass filter, it allows frequency below the specific cutoff frequency to pass through, attenuates frequency above the cutoff frequency, and used for removing high frequency noise or extracting low frequency components. And second type is high pass filter, it allows the frequency above a specified cutoff frequency to pass through and attenuates frequency below the cutoff frequency and used for removing low frequency noise or extracting high frequency components. And type 3 is band pass filter, it passes a specific range of frequencies centered around a central frequency. It attenuates frequency outside the specific bandwidth and used for isolation specific frequency bands in signal. The fourth type is band stop filter, which is also called notch filter. It attenuates a specific frequency range of frequencies while allowing frequency outside the notch to pass through and used to remove interference or unwanted frequency components. And the last type is all pass filter. It passes all frequencies with equal gain but introduces a phase shift that varies with frequency, does not alter the amplitude of the input signal but affects its phase, and used for phase correction, creating delay effects, or implementing phase equalization. What are the time domain parameters for a filter? The time domain parameter for a filter is a step response. It may be good, bad. The good is a good step response indicates that the filter settled quality or smoothly to its final steady state value without significant overshoot or oscillations. Bad is a poor step response may exhibit slow settling time, excessive overshoot, undershoot, or isolations. Um, This can result in signal distortion, inaccuracies in tracking input changes, and instability in the filter's behavior. For overshoot, point good. A low or negligible overshoot is desirable as it indicates that a filter output closely matches the desired response without signaling deviation or transist effect. And for bad point, excessive overshoot can lead to signal distortion, ringing, or instability in the filter's output. It may cause unwanted oscillations or introduce artifacts that affect the accuracy and reliability of the filter signal. In linear phase, the good point is linear phase is considered beneficial as it ensures that all the frequency components of the input signal experience the same phase shift, preserving the signal's waveform and avoiding phase distortion. This is particularly important in applications where phase coherence and signal fluidity are critical. Whereas the bad phase is that nonlinear phase responses such as phase distortion or phase shifts that vary with frequency can lead to signal degradation, smearing of transist signals, and altered frequency characteristics. What are the frequency domain parameters for a filter? Which are roll off, ripple in pass band, and poor stop band attenuation. So in the task 2, plot a signal in time domain and frequency domain along with its magnitude response, and the source code is